welcome to the Probability and Statistics course. Today we are going to talk about distributions. In particular, we are going to talk about discrete distributions. In the next lesson, we can see the continuous distributions. Now, what a distribution is? We have talked about probability functions. We are going to see some particular probability functions that are used a lot, and these are our distributions. So we are going to talk about the binomial distribution and the Poisson distribution. The binomial distribution, we are going to see when we can use it. It's when our experiment consists of n independent trials with only two outcomes. It is important that we have only two outcomes for each trial. We cannot have more than two. We cannot use the binomial distribution in any other case. Also, we are interested in the number of successes out of n trials. Now, although we use the word success, by success we mean what we are interested in. It doesn't always mean something good. It is what we are talking about, what we are interested in. That's what we define as a success when we use the binomial distribution. So we have n trials of an experiment, two outcomes as we said before. One we are going to call success, and this will have probability of occurring p. And the other one, we are going to call it a failure, and this is going to have probability of occurring 1 minus p. Now, the binomial distribution, it is denoted with a capital letter B, and here we have parameters for the binomial distributions. The parameters are the information we need to have for the distribution in order to know exactly which one of this family of distributions we are talking about. So when we generally talk about binomial distribution, because there are some parameters, there is n and there is p, we actually mean a family of distributions. If we are given n and p, then we are talking about one particular distribution. So every time we have a distribution, we always use the notation of a letter to describe the distribution, and then in a parenthesis we put the parameters that we need to define in order to know this particular distribution. So in this case, we see that we are interested in n, the number of the trials of the experiment, and in p, the probability of success. Q is not needed as it can be calculated from p. So the binomial distribution f of x is given here, the probability function is given here, x out of n, choose x from n, p to the power x, q to the power n minus x. And x can go from 0 to n. or it is 0 otherwise. Let's see some examples when can we use or we can't use the binomial distribution. So, first, assume that we toss a fair coin. We assume that we toss it 20 times, so our n will be 20, and we count the number of tails observed. So x will be the number of tails observed. Now we have that the successive tosses are independent. Why this happened? Why do we say this? It's because every time we toss a coin, the probability of a head or a tail doesn't change doesn't depend on what we have observed on our previous toss. So if we have observed a head, it doesn't mean that next time we are more probably going to observe a head or a tail. So we have independent trials. Here we can say then that our random variable x will follow. This is a notation we use when we talk about distributions, that the random variable x will follow a binomial distribution. We said that b will denote our binomial distribution with, we need to define n and p. N for us is 20. Now p will be the probability of what we are interested in. So here we are interested for the number of tails observed. The coin is fair, so the probability is half, and p for us is half. Q can be calculated. In this case, 1 minus half is half. So this is a very simple example when we can use binomial distribution. We saw here we have independent trials of an experiment, and we're interested in the number of successes, in the number of heads, of tails that we observe. Now, let's see another example. Deal 10 cards from a standard deck of 52 cards. Now, x in this case, we say it is the number of black cards we observe. We are interested in the number of black cards. So, the probability here of a black card, the first time we draw a card, will be 26 out of 52. There are half black cards in our deck and half red. Now the second time we draw, the second card we draw, the probability of observing a red or a black card depends on what we have observed before. So, if we have observed a black card before, the probability of observing a black card afterwards will be less than half. And if we have observed a red card before, it's been taken out of our deck, so the probability of observing a black on the second card will be more than half. So we understand that in this case our trials are not independent, and so we cannot use the binomial distribution. We said that it is important that in order to use the binomial distribution that the trials are independent. Now, if for the same experiment, each time we draw one card, we put it back in our deck, then in this case we could have independent trials and we could use the binomial distribution. Let's see what the expectation and the variance of this distribution is. So the expectation of the binomial distribution is given by n times p, and the variance is n times p times q. As we said, as we know now, the standard deviation is the square root of the variance and is given here. We are going to use the binomial distribution to calculate probabilities, see how things we know about the binomial distribution can be used in order to calculate very easily probabilities we are interested in. So, we have 12 components from a batch. Now we know we have the information that the batch contains 15% defectives. What is the probability that there are at most 2 defectives? And also we are going to calculate, we are interested in the expectation and the variance of the number of defectives. Now we see in this example that we are interested in number of defectives. So as a success in this case, we are actually going to say that it is when we observe a defective. So we have that. First of all, the probability of x equals 0. X is our random variable, is the number of defectives, as we said, what we are interested in. And the probability, the p, it is the probability of observing a defective. So in this case, p, as we said before, will be 0.15, as we have said that there are 15% defectives in our batch. So this is p, this is the probability of success. Here we have the binomial coefficient, as it is called, from the binomial distribution. We just have calculated it, is given here. We have to note that this is equal to 1, and we calculate the number. We have 0.142 probability of observing no defectives in our batch. Also, we calculate the probability that we observe 1 defective in our batch. We see here that this remains the same, this becomes 1, and here 12 becomes 11. We have 0.15 to the power of 1, and so on. We calculate the probability, it's 0.301 of observing a defective in our batch. Also, we calculate the probability that we observe 2 defectives, and we find that it is 0.292. Also, we may be interested not what's the probability of observing exactly 0, 1, or 2 defectives, but what's the probability of observing less than or equal to 2 defectives. In this case, we analyze this probability. It's the probability of observing 0 or 1 or 2 defectives. We add up these probabilities, and we have the answer to our question: what is the probability that there are at most 2 defectives? So the probability that there are at most 2 defectives is 0.735. Now we are going to use the formulas we have seen for the mean and the variance for the binomial distribution to calculate what is the mean and the variance in this case. We do not need to prove ourselves every time to do calculations to find what is the mean and the variance. So that's how useful it is if we know that we can use a particular distribution. We have a lot of information about it, and we do not need every time to do calculations again and again for computing, for example, the mean and the variance in this case. So we have that. For this example, the mean will be equal to 12 n, our n, times p, which is 0.15. So there is an expectation of 1.8 defectives, let's say almost 2 defectives in our batch. Now the variance here can be calculated, the square root, the standard deviation we calculate here, the square root of the variance, n times p times q, is 1.236. Now we are going to calculate some probabilities for another example. We are going to work through an example for a binomial distribution. We have that. We toss a coin, as we said before, and this time we assume that it is not fair. So what we have is that the probability of observing a head is 1/4. So probability of observing a head is 1/4. Now we toss the coin 4 times, and we are going to observe, we are interested in the number of tails. So Rn is 4, and our random variable x is the number of tails observed. So success for us will be if we observe a tail. Although we are given the probability of observing a head, we are going to translate it to what is the probability of observing a tail, as that's what we are interested in. That's what's going to be our success. So for this example, our P is going to be 3/4, and Q will be from here 1/4. So X follows a binomial distribution with N 4 and P 3/4. Now we are going to calculate some probabilities using the binomial distribution. We have that the probability of X equals 0 will be, using the binomial distribution, we have N here, X here, P to the power of X, Q to the power of N minus X. So this we can calculate is 1 out of 256. Now the same way we can write down probabilities for X equals 1 if we do the calculations. Here we are going to have that this is equal to 12 out of 256. The probability of X equals 2 will be equal to, we have that this is calculated to be 54 out of 256, and the probability of X equals 3 will be equal to we do the calculations, and we can find that is 108 out of 256, and the probability finally of X equals 4 for all n, it will be, if we do the calculations, 81 out of 256. We see here that we have calculated probabilities for X, for our random variable, equal from 1 up to n, up to 4. For X other than these values, the probability of the random variable taking this other value will be 0. Now, let's do a plot of these probabilities. We have that. We have for 0 that the probability is 1 over 256, so it's quite small number compared to the others here. Now for X equals 1, we're going to put all down 2, 3 and 4. We have for 1, 12. Let's put it up here, 12 out of 256. 4, 2, we have 54 out of 256. 4, 3, we have 108 out of 256. And for 4, we have 81 out of 256. Now, of course, here it's a rough estimate of where the numbers should be. If we measure exactly, you can have an exact idea of how this graph will look, but we observe that it is a graph that it is non-symmetrical. We see all other times we had seen discrete graphs which were symmetrical. In this case, it is not. Let's calculate the mean of our random variable. The mean will be n times p, which is 4 times 3/4, which is 3. Now, we see here our experiment was tossing a coin. If the coin was fair, we would expect that the expectation would be 2. 2 times out of 4, we would expect to have observed a tail. Now, in this case, because the coin is not fair, we see that the expectation is not 2. Let's see now another discrete distribution. The Poisson distribution. Poisson distribution is used when we are interested in the number of occurrences of an outcome in an interval of time. It is an approximation to binomial distribution for small x when p is small and n times p would be equal to lambda, which is it's going to be a parameter of the Poisson distribution. We are going to see next what exactly lambda will be for the Poisson distribution. So we have that. Also, the Poisson distribution has a very important property. It has no memory. So, if a system has been working for a long time, it has the same probability of failing in an hour as if it just has started working. So we understand that we can only use a Poisson distribution if we do not assume that a machine has more probability of failing if it has been working for a long time than when it has just started. If we use the Poisson distribution, we have to have this assumption. Now, the Poisson distribution, it is denoted by the capital letter P, like the binomial distribution we used B. Here we are going to use the letter P. The Poisson distribution, it is used when events occur at random, this is important, at a constant rate lambda. Now that is the parameter of the Poisson distribution, and that's what we have included here. So the rate lambda should be given in order to know exactly which one from the family of the Poisson distributions we are talking about. Now the Poisson distribution, the formula for the Poisson distribution is given here. F of x will be equal to lambda in the power of x e to the minus lambda x factorial for x from 0 up to infinity. Now, we see a difference here from the binomial distribution. The binomial distribution was from 0 up to some specific number n, but for the Poisson distribution, we can go from 0 up to infinity. For the Poisson distribution, we have that the expectation and the variance can be calculated, and the expectation is equal to the constant rate lambda, as well as the variance. The variance is equal to the constant rate lambda. The standard deviation, the square root of the variance, and we can see an example to see how we can use the Poisson distribution to calculate probabilities. We have breakdowns in a system that occur with an average of 24 per year. And the question is, what is the probability that in a particular month, we have to note here that we are asking about a particular month, there is at least one breakdown. Here we gave the rate of the events occurring per year, but our question is for a particular month. So what happens here, although lambda is equal to 24 per year, we need, in order to use it, to translate it to what is going to be per month. So our lambda is 24 divided by 12 months, 2 per month. And so the probability of our random variable x greater or equal than 1, now this would be difficult to calculate if we try to add up an infinite number of elements from x equals to 1 up to infinity, an infinite number of probabilities. So it is much easier if we actually write it as 1 minus the probability of x less than 1. And that it is 1 minus the probability of x equals 0. We see here that for a discrete random variable, it is very important to be careful about equal signs or not. They will make a difference. And so we can calculate this probability, which is 0.8647. Now we are going to work through an example ourselves to see how we can calculate probabilities for the Poisson distribution. So assume that telephone calls arrive at a phone desk at a rate lambda 5 per hour. Now, let's ask the question, what is the probability of exactly 2 calls? Let's say 1 call, we'll make it a bit easier. 1 call in half an hour. How we can calculate this probability? So we have to be careful that here we have our lambda per hour, but the important thing with the Poisson distribution is to make sure that we use the right lambda. We know what we need for our example. So here we need to translate our lambda. For half an hour, what happens? So here lambda will be 5/2 equals 2.5 per half hour. So the probability now that we want to calculate will be equal to e to the minus 2.5. We do the calculations using the formula of the Poisson distribution, and we can find here what this is. Let us calculate now another probability. We want to find what is the probability of one or more calls in 1 hour. So x is the number of calls that arrived, and lambda here, as we talk in an hour, we can use the 5 we had here per hour. So now we can calculate our probability that x is greater or equal than 1. Again, in this case, we see that it's very difficult to add up an infinite sum of probabilities. So we do the trick. We change that to 1 minus the probability of x less than 1, which is 1 minus the probability of x equals 0, and this can be found by calculating 1 minus e to the minus 5 over 0 factorial. And the probability of x greater or equal than 1 can be calculated. So, what we have seen in this lesson, we have seen some particular discrete distributions, the binomial, how it can be used, how it can calculate probabilities, and the Poisson distribution. In our next lesson, we are going to talk about continuous random variables and their distributions. For more information on this lesson, you can visit the web page of Netuno MedNetU project.